Till now, we discussed about the different terms related to the groundwater system. Now, let us learn the sources or origin of groundwater. Rainwater is the mother of all waters. Average annual rainfall in the world is about 1990 millimeters. Highest average annual rainfall in the world is 11,871 mm at Myswaram, located in the Meghalaya state in India. Hence, there is a large variation in the rainfall distribution over the globe. As we observed in the hydrological cycle, a portion of rainwater percolates into the earth strata and forms as groundwater. This process is called groundwater recharge. Groundwater recharge occurs in two modes. One is natural and another is anthropogenic process. What is the natural recharge? Quantity of water added to the groundwater reservoir in excess of soil moisture deficit and evapotranspiration and by direct vertical percolation of precipitation through the unsaturated zone. Average annual groundwater recharge from the rainfall is only about 10 to 15% of the local rainfall. In some places, it much lower than. In unconsolidated, semi-consolidated formations, it may go maximum of 25%. For these recharge processes, several controlling factors exist. Those are intensity of rainfall, climatic conditions of the area, morphology, lithology of the area, structural aspects. These features affects the groundwater recharge. Apart from the rainfall, surface water bodies, irrigation return flow and also contributes considerable amount to the groundwater system. In the overexploited areas or low rainfall areas, to enhance the groundwater resources, artificial recharge methods are being used quite extensively. Some of them are water spreading over the ground surface by channels, pits, small surface reservoirs, injection of water by gravity or under pressure through boreholes directly into the aquifer, roof water harvesting, etc. Based on the availability of the water, local conditions, these methods are used. Next part is, if we want to do the integrated groundwater studies of an area like a basin scale or a watershed scale, these studies can be divided into three major parts. The first part is exploration. The second is development and third is assessment and management. When we need water, we look for possible surface water sources. When the surface water is not available, we look for next alternative groundwater. As the groundwater is available below the ground surface, we cannot see it directly. To see that, one has to make a hole. However, when we make a hole, we may or may not get water due to differential geological conditions. To make several holes is an expensive work. Hence, to identify the water potential zones below the ground surface, several methods are derived based on the signatures on the ground surface or physical properties of the different geological materials. These methods are aerial, surface, subsurface and esoteric. Aerial methods are latest development where you can scan large area using aerial photographs, Landsat imageries, airborne geophysics. Surface methods cover geological, hydrogeological, geobotanical, geochemical and geophysical, etc. Nowadays, geophysical methods are being used quite extensively to locate deep groundwater resources. Use of subsurface methods are limited. Esoteric methods have no scientific base, but some individuals claim that method. However, you are going to study these methods in detail in another module. By exploration, we identify well location, depth of water bearing zone where water is available. We have to make a hole at that location up to the depth to pump out the groundwater called development. To make a hole, either we have to use manual labor or a machine. If the groundwater level is too shallow, dug wells can be made using the manual labor. To make a hole with machine, suitable drilling method has to identify based on the geological formation. To drill a hole in the hard rock area, generally percussion or DTH, down to hole type of drilling used. And in semi-consolidated or unconsolidated sediments, rotary type of drilling is used. Once the drilling is over for the required depth, well construction needs to be done. In the hard rock areas, no specific well construction is required. However, casing either metal or PVC required to top zone till the loose material to avoid the well collapse. Whereas in the soft rock, entire length of bore well casing is required to avoid well collapse. Perforated casing needs to install at places where water bearing strata encountered. Gravel packing also needed at places where perforated casings are used. Once the well construction is completed, well needs to develop through air compressor to remove the finer particles exist in the well. Based on the well depth and water level, suitable pump is needed to pump the water. Assessment and management of groundwater is the crucial part of groundwater studies. First step of the management is assessment. Groundwater reservoir can be considered as an individual bank account with an overdraft facility. If the withdrawal is less than the deposit, there is a positive balance in the account. Otherwise, it is negative balance. Similar way, to assess the groundwater quality and status of groundwater in a selected area, it needs several input-output parameters and change in water storage for few years. Input to the system minus output of the system equal to change in the storage of the system. That is, the input parameters like recharge from rainfall, recharge from the canal seepage, recharge from field irrigation, recharge from lakes, influent from seepage from the rivers, inflow from the other basins are the input parameters. The output parameters are evaporation from the groundwater, draft from the groundwater, effluent seepage to the rivers, outflow to the basin, and change in the storage. This makes the balance of the groundwater in a certain area. Though individual effort is essential for proper utilization of the groundwater, cumulative effort of central and state governments and local NGOs may help in proper management of groundwater resources. Now, let us have a look on water resources around the globe. Like distribution of the lakes and rivers around the world, distribution of basins around the globe is shown in the figure. Purple color areas hold abundant, relatively easily extracted groundwater. More complex basins shown in green color might contain multiple aquifers separated by impermeable rocks or have layers of salt water as well as fresh water. Local and shallow aquifers in yellow color provide only limited quantities of water. Total water available on the globe estimated as 234 into 10 to the power of 5 kilometers cube. Quantity of groundwater available on different continents relatively follow the area of the continent. That is, bigger the continent, more the groundwater resources, but it differs a small percentage.